Is it possible for a three-dimensional figure to have a finite volume but an infinite surface area? In this video, we will show that Gabriel's horn, also referred to as Gabriel's trumpet, which is shown here, does have a finite volume but an infinite surface area. To begin, Gabriel's horn can be created by rotating the graph of f of x equals 1 divided by x over the interval from 1 to infinity about the x-axis. So on this graph, we have the function f of x equals 1 divided by x graphed over the interval from 1 to infinity. And now if we take this graph and rotate it about the x-axis, it will give us this three-dimensional figure on the right, which is Gabriel's horn. These are both the same graph, just shown from a different angle. And now let's find the volume and surface area of Gabriel's horn. To find the volume, we will use the disk method, and therefore the volume equals pi times the integral from a to b of the square of big R of x differential x, where big R of x is the radius function, and because we have rotation about the x-axis, the radius is just equal to 1 divided by x. And therefore the volume equals pi times the integral from 1 to infinity of the square of 1 divided by x differential x. Notice how we do have an improper integral here because we have an upper limit of infinity, and therefore we can write this as pi times the limit as b approaches infinity of the integral from 1 to b of 1 divided by x squared differential x. And now to find the antiderivative, we need to write 1 over x squared as x raised to the power of negative 2, and now we can find the antiderivative. We add 1 to the exponent and then divide by the new exponent, which gives us x raised to the power of negative 1 divided by negative 1. Let's rewrite the antiderivative as just negative 1 over x. And now we need to find big F of b minus big F of a, then determine the limit. The volume is equal to pi times the limit as b approaches infinity of negative 1 divided by b minus negative 1 divided by 1. And now to determine the limit, as b approaches infinity, notice negative 1 divided by b approaches 0. And here we just have minus negative 1, which simplifies the positive 1. And therefore the volume is equal to pi times 1, which equals pi. Now we know the volume is equal to pi cubic units. And now let's determine the surface area. Because we have rotation about the x-axis, the surface area equals 2 pi times the integral from a to b of f of x times the square root of the quantity 1 plus the square of f prime of x differential x. This f of x is just the radius, which again, because we have rotation about the x-axis, is just 1 over x. To find f prime of x, though, we'll need to write f of x as f of x equals x raised to the power of negative 1, and therefore f prime of x is equal to negative 1 times x raised to the power of negative 2, or just negative x raised to the power of negative 2. And therefore the volume equals 2 pi times the integral from 1 to infinity of 1 divided by x times the square root of the quantity 1 plus the square of negative x raised to the power of negative 2. Now if we square negative x raised to the power of negative 2, that gives us x raised to the power of negative 4, which is equivalent to 1 divided by x to the fourth. This improper integral is difficult to evaluate, so what we're going to do at this point is compare this to an integral that's much easier to evaluate. Notice over the interval from 1 to infinity, the square root of 1 plus 1 divided by x to the fourth is always going to be greater than 1, and therefore, if we substitute 1 for the square root, it would give us this improper integral, and again, because the square root is always greater than 1, this integral is going to be less than the integral equal to the surface area. Or we can say the surface area is greater than this improper integral. Let's evaluate this improper integral and see what we get. Because this is an improper integral, we can write this as 2 pi times the limit as b approaches infinity of the integral from 1 to b of 1 divided by x differential x. The antiderivative of 1 divided by x is equal to natural log absolute value of x. We don't really need the absolute value because the interval of integration is always positive, let's go ahead and include it. This is equal to 2 pi times the limit as b approaches infinity, and then the antiderivative is natural log absolute value of x. The limits of integration are from 1 to b. This is equal to 2 pi times the limit as b approaches infinity of, we have natural log absolute value of b minus natural log absolute value of 1. Well, natural log absolute value of 1 is equal to 0, and as b approaches infinity, natural log absolute value of b just gets bigger and bigger and also approaches infinity. And therefore, this integral approaches infinity, and therefore it diverges. Remember, this integral was less than the integral equal to the surface area, and therefore if this integral diverges, so does the integral for the surface area. So to summarize this, we can say if the integral that we evaluated approaches infinity or diverges, then the integral that's equal to the surface area, which is greater than the integral that we evaluated, then the integral equal to the surface area must also diverge or approach infinity, which means the surface area is infinite. So we have just shown that Gabriel's horn pictured here has a finite volume and an infinite surface area. But how can this be? Gabriel's horn can hold a finite amount of paint, but there's never enough paint to paint the surface. This is the paradox of Gabriel's horn.